Well, hello everyone, and welcome to Lecture 3 on SE6046, our Advanced Inorganic Chemistry course. We've had a good look at the F block elements, and we've seen that their chemistry is largely dictated by a partial filling of the 4f and 5f orbitals, and that electron population in these systems and indeed configurations can become quite complicated by virtue of the fact that there are lots of electrons around the nucleus of these atoms. Today, I want to focus on trying to find a way in which we can predict the most stable electron configurations for these elements, because they do get quite complicated. And I'd like to do that by using HUND'S rules to derive something called a term symbol and focus on the derivation of term symbols for the lanthanoid elements. And an understanding, at least, going forward, that these term symbols can be used to describe various physiochemical properties of the elements themselves, such as magnetic, electronic, and luminescence properties, and that these term symbols have important implications for spectroscopic analysis of these elements. So there are lots of electrons around the nucleus of these atoms. The bottom right image I'll show you there is praseodymium. That's a very simple representation of an electron configuration, but you can see that there are lots of electrons that orbit the nucleus. And we've spoken in some detail about how the F electrons dictate the properties of the F block elements and their compounds, and a partial filling of the F block of the F orbitals in both the lanthanoids and the actinoids has consequences for their chemistry. And we can also have unpaired F electrons as well, which will dictate the things like magnetic properties of these elements and their compounds. So with lots of electrons in these systems, it can lead to a very large number of potential variations in the ways in which we arrange the electrons around the nucleus. So it's very useful then to have a method of working out and rationalizing the most stable arrangement of electrons. The first question I pose here is the consideration of electron configuration, and we ask ourselves, is that enough to describe the arrangement of electrons around these atoms? And we particularly focus on the lanthanoids. I show you there praseodymium 3+, which has the following electron configuration, xenon 4f2. So it has 2 electrons in the 4f subshell. Well, in that case, electron configuration tells us that the 4f orbitals contain 2 electrons, but it doesn't give us any information about the way in which the 4f orbitals are occupied. We don't know which of the 4f orbitals are occupied, and indeed it doesn't give us any kind of information about the electron spin on the atom. You'll remember then that we can have 7 F orbitals. They can have values of ±3, ±2, ±1, or 0. And each of the electrons within those orbitals can have a spin of plus or minus a half. So you can see there that electron configuration isn't enough to adequately describe the arrangement of electrons around praseodymium 3+ in this case. Now, if we consider the F block in particular and the small energy differences, particularly between the 5d and the 6s orbitals, the core nature of those 4f orbitals, the slightly less sort of core nature of the 5f orbitals, we realize very quickly that there are lots of different ways in which we may arrange electrons around these atoms, and we call these different ways microstates. Whenever an electron has an orbital angular momentum, there are electrostatic repulsions between them that can have different energies. And some of these microstates may be grouped together as terms, and that's where the word term symbol comes from. And it's the difference in energy between these term symbols or terms that is measured in spectroscopy. We can describe the most stable arrangement of electrons in an atom by summarizing it in something called a term symbol. And this considers all of those factors at play that are likely to determine the energy of a microstate. So on the left there is a generic scheme of a term symbol. There's an S component, an L component, and a J component. The first thing we do is consider the orientation of the spin angular momentum. So we're talking about that ms quantum number here. And this is a very strong interaction. It comes from an interaction between electron spins, which we know couple in atoms, to give a resultant S. And what we do is we sum the spins for all of the electrons in the valence orbitals of the atom under question. Now this value of 2s plus 1 then is referred to as the multiplicity. So for example, if we have an s equal to 1, then we know that that can have ms values, the quantum number there, of +1, 0, or -1, and we would refer to that as a triplet state. So having an S value of 1 tells us something. It tells us about 3 different scenarios in which the ms quantum number would change in each case. We've also got to take into account the orientation of the orbital angular momentum. And this is the next strongest interaction after the magnetic considerations we took on the previous slide. And these couple to give a resultant L, and what we do is we sum these values for the electrons in the atom, and the value of L is designated by a letter rather than a number. So we will calculate a value of L, but we designate that as a number from 0 to 7 on the numerical scale, and S, P, D, F, G, H, I, and K on the letter scale. We then take into account these two things coupling. So the total spin angular momentum will couple with the total orbital angular momentum, and it will give something called a total angular momentum, and we describe that as J, and that can take on the following values. If the atomic orbital under question, or if the shell under question is half-filled, then we subtract S from L, and if the shell under question is more than half filled, then we add L and S to give this J value. Fortunately, there are some quite simple rules that allow us to derive these term symbols relatively simply. The first rule is that we have to arrange the electrons in order to get the maximum value of S, and that will predict the lowest energy. So for example, here I show you praseodymium 3+, and we're only considering the valence orbitals here. So the 4F shell I'm considering here, that's got 2 electrons in the F shell, and in order to get the maximum value of S, we put those as +1/2, and that equals a value of 1. So there's rule 1. I've arranged those electrons in terms of their spin to try and get the highest value of S that I possibly can. I then note my multiplicity, which is 2s plus 1, which is equal to 3. The second rule that we have to take into account is that if there is more than one arrangement of electrons with that maximum value of S, then the arrangement with the maximum value of L has the lowest value. Now I could put those electrons in any one of those 7 4F orbitals, described by the ML quantum number 3210 -1, -2, or -3. And I've arranged them there in 3 and 2 in order to gain the maximum L value. So that is equal now to 5. The final rule then is that if that subshell is less than half full, the level with the lowest J value has the lowest energy. And if the subshell is more than half full, the level with the highest J value has the lowest energy. And here, in the case of praseodymium 3+, the 4F shell is less than half filled, so the lowest level has the minimum value of J. So I subtract S from L to give a value of 4. And there's my term symbol on the left there. The red number comes from my multiplicity value of 3. H comes from my value of L. And 4 comes from my J value. We can do one more here. I show you here now europium 3+, which has 4F11 F subshell. I gain a maximum value of S. There are 3 unpaired electrons there, all with a spin of +0.5, so that is equal to 3/2. The multiplicity then is 2s plus 1, which is equal to 4. Rule 2, I'm gaining a maximum value of L here, so I sum up electrons in those orbitals. That gives me 6. Rule 3, the 4f shell is more than half filled here, so the lowest level has the maximum value of J, and I add L and S this time, and that gives me 15/2. So there's the complete ground state term symbol for europium 3+, 4I 15/2. So there are some exercises for you to complete and have a go at these yourselves on Moodle. I've put the questions and answers up, so give those a go, and I'll see you next time.